So now I'm going to go through a couple of examples uh, aligned with this week's lectures on the code. First, I'm going to create a camera in one of the previous projects, which I'll show you. And also, we'll talk a little bit about instanced rendering, which wasn't covered in the lecture this week. However, the idea is probably pretty familiar to you already. Once you create a VBO and a mesh that you've created in the previous assignments, you can imagine that you don't need to do another one. You don't need to create it again on the GPU. So why not just render the same data off the GPU multiple times? So in this example, we're going to take the previous one of the previous examples, build into it a kind of camera model, like a camera object, which we'll then use to demonstrate projection matrices and the MVP transformations that we've been talking about. And then we're going to also add to that some of the other stuff like instanced geometry, so we can have multiple of these things. And then we're going to go through some of the examples in the repository as well really quickly to kind of show you, how my 5-minute code compares to a slightly more evolved and mature example. So yeah, let's get into it. So first I'm going to do something that I haven't done in these examples yet. I'm going to actually copy and create a new project from an existing one in the repository. So this is actually pretty straightforward, but I've never actually done it in a lecture, so I'll do it really quickly. So all I'm doing is I'm taking the C14 folder and I'm copying it and I'm pasting it. I'll get a copy. And what I'm going to do here is I'm going to call this my example camera and instancing. And then I'm going to call this C14EX. And then what I'm going to do is I'm going to grab that text, which you'll see why in just a moment. So I'm going to go into this folder, and you can see here's the previous project. I'm going to rename all of these VC projects, like Visual Studio project files, with the correct name. And then finally, I'm going to open up the VCX project file with something like Notepad. Let me zoom in a bit so you guys can see. Oops. There we go. And I'm actually going to search for C14, which is the copy. And I want to change the situations where this shows up in here to this new value. And let me find that's all we got. We just got those two. Let me open up these two as well in here. And you'll see, I think C14 will not show up, and here neither. So that's all we had to do there. Yes, we have to save it. Great. And then also, one thing we want to do is we want to open up this solution here. And you'll see a bunch of stuff. So let's find C14, which is right there. And what we're going to do is we're going to copy this little entry and, again, change this, all the instances of that. Now the GUIDs are not gonna, we're not gonna create new GUIDs. We're gonna have a repeat GUID here, but that won't really be a problem. So if I open up my solution now, Visual Studio 2019, you'll notice that there's a new project down here, C14EX example camera and instancing. And I'm gonna drag this into this filter here so it's a little bit closer. So this is going to be right below the quaternion example. So let's set that as the startup project and run it. And let's see that nothing broke. But you can see really quickly in like just a few minutes, I was able to do that and to create a project from an existing one. So if you have any issues with that, I figured I'd just show it really quickly. So cool. So now we're back in this example where we last, we were showing some of the funky issues with lerping rotations. So let's quickly get rid of some of that old code. If you remember, we were in app class.cpp, and this is where most of the magic is happening. And we're going to, for the time being, not have anything we're going to get rid of this code here. Yeah, I'm going to get rid of this. And that's that. And this should just be normal. Nothing should happen. Another thing we're going to do is add to render list. What does this do exactly? This takes our code and adds it to the render list for this project. We don't really want that. We want to be working directly with our fragment shader like we were doing before. So let's quickly see what's going on here. This is another thing you might have to do if you create this project from one of these. You don't, let's find this. We want to be using the basics, not the simplex. So what this will do is we'll switch over to basic X. And again, the difference being, and you can actually delete the simplex stuff, the difference being that this is now going to use this code in here versus using the pre-built binary. So let's just really quickly run this and see that it still works okay. And we're having all these errors. Simplex is not a class, yada yada. And so what we want to do here is we want to switch all of those situations to basic X. Let's build it again. Oops, I don't want to build the whole thing. Let's just build this project, which you can do with Control B. Okay, let's get rid of the model for now, because the model's not in there. We don't need the model anyways. And let's get rid of this. And let's build. Oop, we gotta get rid of this one. This is just me trying to get to a base point, and this is kind of, I'm also trying to help you guys get to this point as this is necessary. So I'm just switching this out, all the simplex with basic X. Looks like we got the last ones. And let's run it, and hopefully we'll see the same stuff. Cool. So about the same. Great. So now we need to create some meshes, like create a mesh. Let's make sure we can still do that. And let's do a mesh, pmesh equals null pointer, and then pmesh equals new mesh. And let's see what are the options that we have here. Just two options. So let's check out mesh.h, which is in basic X, and we'll see here that we're able to add quad, add tri, render wire, render solid. What are our options? These are all So we can create a mesh. So let's do a new mesh, and then pmesh add cylinder, or let's see. Add quad. This is getting a bit out of hand. So I'm not a fan of this. Let's get rid of this. We have my mesh from the previous example, so let's do that. So my mesh, p mesh equals new my mesh, and let's see what my options are here. I haven't looked at this code in some time, so it's the same. So let's do the following. Instead of this, I just want a cube, you know what I mean? So back in our rotations example, we had a my mesh where we created a generate cuboid. This is what we want in the primitives. So let's really quickly go back here. Do we still have that? Yeah. Great, we can still do generate cube. So let's go back to our app class, and let's create a my mesh p cube equals new my mesh, and then p cube generate cone. Why not? With a radius of 0.25, a height of 1.0, 10 subdivisions, and a color of, you know, let's do basic x vector 3, 1.0, 1.0. Let's make it red. 1.0, 0.0, 0.0. Great. And here, we're not going to render, well, we can render that fine. Let's actually make this cube in our app class here. Let's call this cone. Let me zoom in a bit so you guys can see hopefully a little bit better. And then we're not going to do that. We're going to, whoops. Great. Right, so I'm going to change this to cone. And then here, we're simply going to render. And here's the stuff we need to worry about. Well, we want to render it, but we need to provide a projection matrix, a view matrix, and a model matrix. So, where are we going to get this information? Well, let's initially just start off with kind of faking it for now. So let's create a GLM matrix for the transposition. So let's do auto. Don't use auto, but I'm doing it so I can code this quickly. Mat for model, and that's going to be a GLM transpose matrix, where we are going to let's do a translate matrix, whatever, and we'll start off with the GLM identity. No. Mat for I always forget. I always forget all the stuff, so I always look it up. Identity. So just like this. And then we're going to do a vector, GLM vector 3, like that. So that's our model. Great. Then we want our view to be basically -5. And then finally, our projection. Let's start off with a GLM orthographic. And you'll notice here you've got a T left, T right, T bottom, T top. Or a T left, T right, T bottom, T top, T near, T far. So what we want to do is we want to figure this out from a couple of different things. But let's assume that our window size, what's our window size? We can look this up, right? Our window size is going to be set in main. So we have 1280 by 720. So right now we're going to hard code this. In width is going to be 1280 divided by 2, or in height is equal to 720 divided by 2. And we'll do our float near. Near plane we'll set to 0.5, and far plane is going to be set to 1000. And then width, height, near plane, left. So the left is going to be negative width. The right is going to be positive width. The height, the bottom, I'm sorry, is going to be negative height. And the top is going to be positive height. And then the near is going to be that near plane, which is negative the 0.5, and then the far plane is going to be the far plane. And we're going to get an error here because it wants us to have a floating point value for these. And if you really want to be explicit, so nothing blows up in your face, there you go. So this is sufficient to at least get us to be able to call this render call per the mymesh type. So this isn't the mesh that we developed in previous lectures. This is what's part of the basic X code base. In this case, it's still in this code. So you should be able to then just pass these variables in directly. So my projection matrix is the mat for projection. My view is the mat for view. And my mat model is mat for model. And with a bit of luck, this will compile and hopefully run. Will we see something? We will see. Looks like no. Looks like we do not see anything. So there's a couple of things that we might be doing wrong. The view matrix might be inverted. So maybe we're behind the object or something. No. Does not look like that's the case. The other thing that could be going on. What else could be going on? Let's take a look at the quaternion example, which is doing this, right? Let's make sure that we're in the right code. So here we can see that we're loading the model. Let's take a look at rotations because that's doing something different. Okay. The issue, one of the issues at least, is that No, we're doing it in the right place. No, that's correct. Let's see here. Rotations. Alright, I'm going to pause while I figure this out. Okay, and we're back. So this took a little bit of finicking around, but this is sort of the code that you need to use to get the orthographic projection working. And let me kind of go through what was done here, which is, I think, kind of important. So first thing, I'm going to move this code up here. So the first thing I did, and this is already kind of skipping a step in terms of what we need for our camera, we changed this a little bit to a Z position. The Z position now is used by this matte view matrix, and that sets our camera position in the Z, in the depth. But that's used for this, in that in the next step, what we're doing to create the orthographic projection is we take the width of the window. By the way, if we want to be a little bit more systematic, we can use the system, and we can get the window width. We have to cast it because, you know, C++ or whatever. And we can also do float MP system get window height. And keep in mind, MP system is just a singleton of our system here, and it should be initialized. We'll find out. Let me actually check. But that way we get the ratio of the two. And here, yeah, M system is there, so you can kind of see if we step through it. Width is going to be 1280, height's going to be 720, and the ratio, the aspect ratio, is 1.77, blah blah blah. Then we set our near plane to 0.1 and our far plane to 1000. And now the calculation is a little bit different for the orthographic projection. In this case, our left, right, if we take a look at the definition of the orthographic projection here, the left, right, bottom, and top, right? These are the values that we need to create it. And so the left is going to be the ratio times the Z position that we are at, and the right is going to be kind of the equivalent of that in the opposite way. As you can kind of see here, this is the values that we need. Cool. And you can see the values that are being figured out here to actually calculate the matrix. You can see they're pretty simple. It's just really a scaling of everything to this aspect ratio that we've defined. And then similarly, we're setting the kind of left and right to be the negative Z, to the top and bottom to be the negative Z and the positive Z position. And what you can kind of think of this as is this is kind of where we're going to cut things off, if that makes any sense. Then we've got the near and the far plane. So now when we run this, we'll see the cube. A really important thing to show, if we move closer, it's still going to show up the same way. Or not show up at all, apparently. Oh. This doesn't seem right. Okay, so right now this is not correct. Like, this shouldn't work this way. What we really want to see is we want to see a left and a right thing. So let's try to get rid of this Z position in here. Let's see if this is going to work now. some reason, I think what we're doing is we're cutting everything off too small. There it is. Yeah, I'm not having the best time here, but what we can do is we can go width divided by 2, width divided by 2, negative height divided by 2, height divided by 2. What's it complaining about? No instance of double, double, double. Great. There we go. That should fix it. And let's see if we see something. It might be too small for us to see. There's a little dot, really tiny over there. You can't quite see it. So what's important is when we're doing the orthographic projection, the reason it's so small is we've now mapped an orthographic projection that is the size of our screen, that is the same equivalent units as our screen, meaning it's 1280 by 720. So I'm only going to show this for demonstrative purposes because I'm going to move to the perspective matrix in a minute. But if I was to change this, I want it to be 10 units wide by 20 units, then we'll see a thing on my screen that's approximately 10 by 20 pixels. Or not. Oh, I think we might be inside of it. So we have to move it back. We have to move back a fair bit more. And I thought we were making a cone. What's going on here? Everything's weird. Let's see here, and let's make it bigger. Let's make the radius even bigger. Now I'm... Right. So, in short, not entirely... Let me take a break right now. Let me pause, and then I'll be right back. Okay, so I'm an idiot. That's okay. You guys get to learn from my mistakes. The code in generate cone is removed from basic X for your enjoyment, because this is something you had to do for your assignment. So let's go back and fix that so that we can actually do this without me having to write all that code again. The way we would do that is we go back to the app class, to definitions, and we would use the simplex instead of the basics. And let's go back to our code here and our definitions.h. And what will happen is a lot of code will break again. Apparently not. Apparently, oh, wrong project. Let's close all but this so we can know what we're working on. And it'll give me a bunch of stuff. Simplex. Down here. Let's build it. There should be one or two more errors. Great. And now, hopefully, we'll get a cone. Cool. So at least we fixed that. So you'll notice now I've got a cone, and this is an orthographic projection, and it works relatively well, which is neat. So say I wanted to move my camera, move my orthographic projection around, and you can see here now I'm doing this width, negative width, positive width, and so on. I'm moving backwards and pretty far. I'm going like negative 100 because I don't want to be inside of the cone. If I am, I might not be able to see too much. But you'll notice now if I get closer, or even if I get farther, so I'm going back 500 units, it's not getting smaller, it's going to be the same size. And so hopefully that's demonstrative of what an orthographic projection is doing. It's basically taking the points and projecting them directly onto the screen. So say I'm making the cone like 250 tall, it should be approximately 250 pixels tall. So if I did a measurement when it was perfect, I should be able to see that. If I make it, really big, it should eventually be bigger than get close to the size of my screen. Cool. And this really comes down to the sort of scaling that you're using. Notice that if I get closer to it, if I get too close, let's say at 100, I should start to see kind of clipping happen, because my near plane, I'm now so close to it, even though it doesn't seem like I'm close. The issue is my near plane is intersecting the geometry. So that's the thing about orthographic projections. The math is really simple, but they're a bit surprising in the way that they behave. Okay, so let's we've had our fun with the orthographic projection. Now let's create a perspective projection, and to do that we're going to use the GLM perspective function. We're going to use a 60-degree FOV, but let's pull this out. Let's call this FOV, and we'll call it 60.f degrees. And then the aspect ratio is going to be this ratio we've already defined up here, which is the ratio of our window width and height. And then finally, our near and far plane. Near plane and the far plane. And in a way, you can kind of think like this is a lot simpler. We're probably not going to see much because it's huge. We're super inside of this thing right now. So let's make this more reasonable. Let's go back to our small 0.5f by 0.5f cone with and let's go backwards only about 5. Position of 5. And you can see now we've got a tiny little thingy there. And it's rotating in a much more kind of interesting way. Why is it rotating all weird? It's because we're rotating the view matrix, because I'm an idiot. Yes, there we go. This will make a lot more sense now. Before we were doing it in the view, that doesn't make sense, so cool. Now we've got our cone rotating about itself. And we can kind of increase this a little bit to make it a bit more interesting. And let's make the cone a little bit bigger so we can actually see something. Because we're pretty far away. So let's get a bit closer. Oh, now a bit too close. Let's back off. Okay, so now we've got the MVP working. You'll notice this warping. And that is because I think I did the aspect ratio backwards. So let's fix that. So our ratio is the width divided by the height, which is what we needed for the orthographic, but what we want is height over width in this case. The FOV can also play a big role, although I may be doing this wrong. So actually, that's not the issue. The issue, our aspect ratio is correct. Our issue is our FOV is expressed in radians, and then, so we need to convert that to, let's do this up here actually. Which will probably make things make more sense. Great. So now we don't have that warping, but it's way too big. That explains why everything was so small before. We'll have this, and we're 6 away. Great. Perfect. So we already actually have a pretty much functional camera, right? So say I switch this over to a vector 3 camera position is equal to a vector 3 0.0f -10, and I replace this now, right? This will work, and if I add, for example, a camera position translate or increase x by 0.01, and notice I made this into a static variable, so it'll repeat itself. Oh, it's too fast. Happens way too quickly. So now you'll notice the object will, what? Oh, that's why. So now I'm at -10, and I'm moving in x. And you'll notice that the object, well, let me turn off that rotation, which is probably not helping visualize this. But you notice the object will start moving to the right. And the object is moving to the right, but we are moving to the left. And I think that's sort of the kind of thing about the view matrix, is realize that the view matrix is going to be doing the opposite to what you see. So when you move to the left, you're actually moving everything else to the right. And so what you really want is sort of the inverse of the position. So technically, say I want to be, so let's put this object at 0. And let's get rid of this translation. And let's put ourselves at 2.5. If we're at 2.5, then what's going to happen is the object is at 2.5. That's not what we want, though, right? If we were at 2.5, that means that we had moved this way, but the object should have moved the opposite. So one of the things that you have to do with the translation matrix is you actually have to invert it. And now if we inverse this camera position, great, we have to be at +10, right? We're at 10 and everything else is at -10. Now the world is the correct orientation. So moving an object to the left will move it to the right for us. And that makes sense, actually. This is where it gets a little bit wacky. But it's important to kind of know about that. So okay, cool. We've got the camera position. We've got the view in the position. But what about the orientation of the camera? So what we want to do is we need to have a sense of where the camera is looking. So the camera could be looking up. It could be looking down to the left, right? There's an orientation associated with our camera. So let's create a quaternion. that is representative of our camera orientation. And we're going to initialize that to just a quaternion. And then let's say we're going to play with this gimbal example, right? And we're going to say we want to have Euler, numbers. This is for now. In the future, you might not actually operate this way, but let's do this, the x rotation, the float y rotation, and the float z rotation. Great. And from this, let's quickly take a look at our old code, because I forgot how to do this with this. We just want to pull off the quaternion from the Euler angles, which is not in here. Okay. Great. Right, let's do this. So, GLM vector 3, Euler angles equals vector 0, 0, 0, and then we're going to go Euler angles. Why do we have... Let's just do this. I'm not sure what the deal is. Oh. Okay. Well, I'm going to pause while I... Okay. Much simpler than I thought it was. It's just plot Euler angles. Great. And then all we have to do, and let me add this to, let me do mat4 view is equal to the inverse of mat4 view. So then we don't have to worry about it. We'll just do it at the end. Great. So now we've got the camera orientation quaternion. We have to create from that a matrix. So actually, this is the beginning of our matrix. We're not going to scale our view. We're going to keep it the same size. So the rotation, we want to rotate and then translate. We don't want to translate then rotate because then things will be incorrect. And so what we want is a matrix for mat4 view is equal to GLM rotation, the Q camera orientation, and we also want to have start off in identity and do this. Static camera, and then great. We're going to keep that there for now, and then we want a rotation where we can take a quaternion in the math of which is not immediately obvious. So again, let's go back to our code from the previous thing here where we used our quaternion. to rotate. Where are you? There you are. And right here, two matrix seems to be the equation, the function that I'm missing here. Well, actually, we don't even need to do this. We just have to start off there. Great. And with a bit of luck, there we go. Now, how do we know that this is working? So let me make this Euler angles static. And so now let's increment x by 0.01f. And so in this case, we are rotating up the x-axis. So what we expect is the cone to go down. Oop. Great. So why are we rotating the model? That is the question. Okay. So I once again misled you. Okay, when you're rotating a model, you want to rotate and then translate it. In the case of the in this case in the case of the view, you want to translate it first, then rotate. Because if you think about what's happening with a camera, is first you move somewhere and then the world rotates about you. And so we do have to flip that around. Great. Sorry about that. Cool. So now what's going to happen is we're going to, of course, be backwards again. We are demolishing our thing here. And here we need to go identity. Not as simple as just moving it around. There we go. Okay, after that long-winded thing of me screwing this up 3 times. So here's what we're doing. We're moving the object to 0, so we're not moving it at all. We are then positioning the camera at 10, which means that our object is at -10. And we're looking down the -z axis, and we're moving the camera also to 2.5, meaning that our object is -2.5. And then we're translating, we're rotating on x using a quaternion by looking up. And when we look up, and I reduce the speed, when we look up, things go down, as you can see. So this is us looking up. Similarly, if I'm looking to the right, the object will go left. Sorry. This would... I'm looking into the -z, so this is when things get a little bit confusing. Because we're looking into negative, and so everything kind of is opposite than what you expect. And then finally, z, if I'm rotating about z this way, everything should go that way. It's very slow, so I'm not sure that, oh, sorry. Yeah. So because we're looking in the negative Z, this turns into that again. So you can kind of see how the versus whether you're doing a right hand or left hand sort of operation, which direction you're looking, makes a really big difference. So yeah, like for example, if we put this at -10, but we want it to point the other way, let's do that. So now we're going to be at +10, but we're going to look backwards. Oop, that's not going to work. I'm going to... right. I'm doing this not on Z, I'm doing it on Y. Great. So now when I rotate by Z, it'll go in the right way, and if I rotate by Y, for example, if I'm looking to the right, things should go to the left. Oh, well, I'm still in this sort of funkadoodle thing. One way to deal with this is to invert your quaternion. Maybe not. Okay, forget what I said. But you can kind of see the... if you try to use quaternions for cameras, it gets a little bit annoying. But just generally speaking, you do want to kind of keep in mind that the direction you're looking matters. The convention that you're using matters. The position of the object respective to the position of the camera. All these things matter. Right, like for example, if I put my camera position at 10 and I put my object at 0, I need to rotate by Y a fair bit to be able to see my object. Sorry, if I'm -10. If I'm at -10, then I'm looking down the positive Z-axis. Might have to speed this up a little bit. So I recommend when you guys work on this, just kind of play with it. And you can see that you're rotating about the positive Y, which is actually this way, and then objects go the opposite way. So you kind of have to visualize all these things. Okay, cool. So okay, let's do something with this. Now we've got a fair bit of code here. We're not going to manually change all this stuff all the time, and let's talk a little bit about putting all of this functionality into effectively a class of some kind. So in our code, which let's close out everything else. In our code, let's pretend like we have I know we have this camera manager we're not going to use, we're going to create our own camera. And let's create next to the cone here, my camera. Let's assume that this exists. Great. And let's create a header. That is my camera.h. just a simple little hack. And a camera is actually quite simple to build. And let's start off with our constructors, our destructors, which we don't really need much of. And we do need some of the definitions in here, like the GLM things, which where I like to not memorize these things if I can avoid it. So let's looks like they're nowhere for whatever reason. Or maybe they're in here. Whatever. We'll find out soon enough when our code yells at us for that. And so we want to have a vector 3 m point origin, and this is going to be in app class. Here we are. Great, so let's stick that in there, and then we don't have too many issues. And what we want to do now is great. So now we have this code, and we want to be able to get a matrix for get view matrix, and matrix for get projection matrix. And why are we cool? Awesome. And our camera needs a position so far. And that's where we're going to just copy all the code that we've already written into this and see that it still works. So my camera.cpp include my camera.h, and little fun thing here, let's start to propagate. Oops. Point origin, this doesn't do anything, and for now this doesn't do anything either, and we're going to start moving the code over. So the first thing we do is we want to create our camera is equal to new my camera, and we're going to start it off with a vector of 0.0f, 0.0f, and -10. So we're going to start off at -10. Great. And then what we're going to do is we're going to set here MP camera, get projection matrix, MP camera, get view matrix, instead of you know, the prior thing. Now my camera, it doesn't really know what to do. Doesn't know how to get to it, so we have to, oh, it's right here. I'm not sure why it's mad. Is inaccessible. So this always bites me in the butt. Classes by definition are private, so you have to define the constructor to be public. Great. So now this should all compute, but it won't do anything, which is bad. So let's take all of this code, except for the model, and get it out of here. And now we're going to put it, for now, in the view matrix. And then we're going to take the perspective related stuff and we're going to put it in here. So first thing we're going to notice is that our camera doesn't know the width of our system. So we can either pass it the my system and do this every time. And that's one idea. So let's go back, and MP system, my app class is this simplex singleton. And so what I can do is, yeah, we can do it that way. Let's pass to it the P system. And then what we're going to do is we're going to hold on to that. So this is a bit of a quick hack. And what's nice about that is now, as long as we pass to it this MP system, it should have access to all of that as well. So you'll see now that this won't complain anymore. Now, camera position, oh, right here we have to add that MP system, and then again, MP system, P system. Whoops. And we'll have to include, we have to include simplex in here. So how do we include simplex? Simplex.simplex. Great. So now this should all, no more yelling. Great. So what we're going to do is we're now going to return map for the view. You can see here, instead of using the camera position, I'm instead going to use MP point origin, so I don't need that anymore. And this is important. I'm going to take this and I'm going to put it in my Euler orientation. And I don't need static. And then here I can do that, and I'm going to get rid of that bit right there. And here I'm going to add an optional vector 3 v Euler orientation equals vector 3, and all that's doing is it's creating a default variable. So if I don't pass it, it just will ignore it. And now here, Euler orientation is going to be equal to v Euler orientation. Let me rename this because I like my naming conventions. Great. And now, I don't even have to do this, I can just return here. And so now it's calculating the width, all this stuff should work, and now my camera class is now operating inside of the context of here, where I'm using my camera class to get my view and my projection matrix based on this position. So let's see if this works. And allegedly, I should see something very similar. Or not. So what is going wrong? Did I do that whole thing again? With a 10, negative 10? There we go. So now I'm at 10. I'm looking at it. And so now you can see I can change the position of my camera by creating a camera at the position that I want it to be. So now I'm going to be closer, or I can be farther away. Great. So let's go back to 5. Now you can imagine that I want my camera to react to my user input. I want to move around with the keys. I want to do that kind of stuff. So like what we have is already pretty much it. Like we don't need too much more. Like we're already operating on rotation and position and a perspective. But we might want to pull a few things out. So first thing is the FOV. We might want to change the FOV to be a member variable. And the reason for that is we might want to change the FOV. So for example, we want to do something like my camera set FOV, and then we do a mem FOV is equal to FOV. Why would we want to do that? Well, let's check out some cool effects that we can now apply. So, well, let me make this public. So I don't even have to make a function to call it, but like, say I wanted to mp camera dot FOV plus equal to 0.01, and what this will do is it will increase the FOV every frame by a little bit. You'll notice that it'll get smaller because we're creating, and eventually it gets too big because we hit the negative. We got so big, we're now going backwards. Okay, so you can see you can do some fun things there. You might want to be able to adjust the FOV. Also a good reason to make it private. If you don't want to be able to do that and you want to be able to test the values right, so like set FOV, we can say if FOV, we can do this, for example, GLM degrees, radians, right, for example, and then if FOV is greater than 180.10, then FOV is equal to 180. If FOV is less than 0, then FOV is equal to 0. Or maybe we can do even like a minimum FOV of 10. I believe that the C++17 or something has clamp, where you can, I think, do, yeah. You don't want to have maybe 180. But I forget what you have to include to do it. Oh, algorithm. Whatever. Saves you 4 lines of code, right? So now you can sort of set the FOV in a way that's a little bit more effective. What are some of the other things we might want to do? We might want to move to the left, move to the right, move up, move down. But so here's now the issue. What does move up, move down mean? What does move left, move right mean? And this is where actually cameras get a little bit more complicated. So we can obviously change our origin. We can set x to the left, x, what value of x, and if we want to go up or down. But that's not necessarily what we want. We want to be able to move forward, and moving forward may be meaning we're looking in a particular direction, and not necessarily. So let's start off with rotation, because rotation isn't something that is view dependent. If we want to look up, we just change x in a positive direction. We want to look left, we want to move that we want to rotate by the y. So let us do a rotation. Rotate view, and I'm going to do delta x and delta y. We'll see why in a minute. And so all I'm doing here is I'm going to my x plus equals to delta x and my view orientation dot y plus equal to delta y. So like, why would I want to do that? So here it's simple. All I have to do to move around, so my camera, rotate view, by, say, 0.1f, 0.0f, and now I should be rotating by x. Not sure why it's rebuilding everything, but that's okay. Right? Or if I'm rotating by y, I'll look to the right, yeah, to the left. Perfect. So why would I use this? I don't really want my camera to constantly be looking all over the place, after all. Well, what if I used my app controls? So let's take a look at this function, at this file. Here you can see the BFC and all this stuff. So process, mouse press. So it looks like when I'm hitting the right button, this flag turns on, MBFPC. And that might be pretty useful because now, let's take a look. I want to look to the left when I'm right-clicking and look to the right when I'm right-clicking and up and down. And so here is our camera rotation stuff. This is the code that already does this, of course. But let's see. You can see here, camera rotation is what we use to do it for the render list, but we have our own camera. And so all we have to do now, if we have our camera manager, as you can see here, it's already doing it. So what we can do is just kind of hijack this. And we want to change the yaw, the Y. We want to change the X and the X. And that's it. This is our camera hijack. What this code is doing is it's determining the delta of the X every frame. So when you right click and you move, it's going to recenter the mouse. And if you want to read through this code, you can kind of see it's getting the window size, it's figuring out the respective distances, it's figuring out the deltas, and then we're converting that into a speed of rotation for our camera. And if we do this right, now hopefully when I right click, you can see I'm rotating my camera left and right. And you can kind of see that the skybox moves at a different rate than our camera does. And look how quick that was, right? Like I can get that and work it. Notice that we've got this gimbal lock that we've talked about. I can't look up anymore. And we get into this funky scenario where our thing is in a weird place because we're using quaternions to do that, but that's okay. So yeah, right now we're not using the same camera for the skybox and for our object, so keep that in mind that you kind of want to use the same for both if you want things to kind of stay aligned. Another option too is instead of using a quaternion like we're doing, you can create a Euler rotation matrix directly. That's another option. Yeah, I'm not going to go too far into this. Like this is what your assignments should be teaching you. And if you have any questions about it, please bring this up in office hours. So now we have a rotation of our view, which is cool. And our Z is never going to rotate because we're not doing that for this camera system. So now we want to be able to move forward and backwards. So let's create a couple of things like that. So let's create a function void move forward, float value. Let's actually call this forward and float sideways. And there's a reason why I'm doing it this way. And I'm just going to call this move. Just one less function. So we have just one function for move. If you were building a full camera system, you probably would want to be a little bit more interesting with your functions and a little bit more complex. but for now we just want to be quick about it. So all we have to do, right, is we have our point origin, right? If we want to move forward, we just do point z plus equal to forward, right? And point origin x plus equal to sideways, right? So that's it. That's all we need to do. And let's go back into our app class controls, and we want to process the keyboard here. If we, let's add a WASD situation here. So we already are handling this. So we're just going to hijack the code. Oops. That's already here to some degree. And we're going to move at speed, right? Oops. So we're moving forward, we're moving negative, now we're moving sideways. And so you'll notice something, right? As soon as we do this, we're able to move around. It's pretty straightforward. Because what we're doing is we're changing. We're going a bit too fast here, so let me slow this down by, our multiplier is, I see, that's not really the case. F speed, let's slow down by 25, by 4 times. So one thing we'll notice, forward and backwards are backwards. So if I go forward, I actually go backwards. If I go backwards, left and right seem to work okay. So easy enough to flip those around. And again, the reason is because we're looking to the negative z. So it's really about conventions and what you want to do there. So cool, now we can move around. And notice I'm moving correctly because left and right, I'm strafing or whatever you want to call it. I'm not rotating, that's what I do with the mouse. But so let's assume I'm over here and I'm going to look over at the cone. If I hit forward, I want to go towards the cone, but I'm not going to go towards the cone. I'm going to go in the positive x and y. And so my translation is not relative to my orientation. Okay, so now that's the harder part of a camera, is building that bit. And the way we do it is by way of effectively a orientation basis. And the orientation basis allows you to basically there's a couple of ways to do this, and the orientation basis is the best way, but perhaps I'll just use the look vector, and that way, if I know where I'm looking, then I can move in that direction. I can add a variety of different vectors to really understand which direction I want to go. If I'm looking, then I also know which direction is to my left and which direction is to my right. So I have to create a new member, vector3 mv up. And this is actually more of a utility vector, as you'll see in a minute. And up we're going to define as being up in the direction of y. So it's always going to be the same thing. And then we're going to create a vector3 mv forward, or look. I'm not going to define that yet. Actually, I will, because we're going to be initially looking into the negative z. And then we're going to define a mv left. And that one, we shouldn't, but we can define it as being, if we're looking backwards, so if we're doing the right-hand rule, x, it should be 1, but we're looking backwards into the negative z, and so that should be negative 1, negative x, 1. So let's start off with this very simple set of vectors, and let's change our move function. Instead of doing this, we're going to, our endpoint origin is going to be plus equals to forward times our mv look, and then our endpoint origin plus equals to sideways times mv left. And keep in mind, right, look is just the negative z, and left is just the negative x. So right now we're not rotating those or anything. And let's see if this works. And we should have the same behavior as before. So now, well, great. So the look is should be fixed again. Oops. We flipped this before to compensate for this issue. So now we can flip it back. Yeah, I think 90% of graphics programming is playing with negatives. So now forward, left, and right is also backwards. Maybe in this case, let's do something. This is what we should actually do. To be consistent, the way we calculate the left, so you've got a vector up and a vector forward. And to get the correct left, you just have to have the cross product of those. And so we can actually calculate that here. MV left is equal to MV up. Or how do we do cross product? The GLM cross of MV up and MV look. And hopefully now the conventions should all line up. We don't have to juggle too many negatives everywhere, and keep that in mind. So forward, and we're still backwards on left and right. So that's largely because of the fact that we're looking into the negative z. And that's annoying, so let's go negative, well, we can just trick it here. There. So now left and right are correct. But again, if I look over at my cone and I go forward, I'm still not going to rotate that. And so what we need to do is actually rotate our look vector we need to get the rotation matrix like here. So this is our orientation matrix. And rotation. Actually, we don't even need to do that. Yeah, no, we'll keep it. This is good. And then we're going to multiply our look vector by that. Now, this is one way to do it. Our vector 3, this is a vector 3, however, this is a 4 by 4. So what we need to do is we need to create a vector 4 out of that with a 0. So we don't want to translate it. But actually what we want to do here is we want to create a vector 4 vlook, and now vlook, we're going to do that. And to get the left, vector 4 vleft is going to be equal to the cross product of v. First of all, we have to make a vector 4 out of our mv up and 0, and this vlook. Why is this throwing a... Okay, I guess I can't cross product a vector 4. Yep, so that'll work. Okay. This is a bit of a hack, but this will work for now. Oh. Okay, that's better. So now I'm converting this look. Now I have the V left, which is the cross product of that. And again, I'm going to just do this here. And V left. And here. Cool. Now you can kind of see, in a way, all I'm really doing is I'm creating a basis. I have the up, which doesn't change, and left and right. And it's almost like I'm rotating that and creating a new transformation matrix from that, which is exactly what's happening. It's an orthonormal basis that is being rotated, and then that's how we know to go in the particular direction that we want to go. Okay, so I cannot convert what I want to convert, so .x. Again, this is not my favorite way to do this, but you know, GLM is great, but it doesn't do everything, and sometimes you do run into issues. Let's see, 67. I see. Right. Let's see if we can do this with everything is threes. Looks like we might be able to. Yeah, it looks like we might be able to do everything with threes anyways. So we might not need to do all of this fancy stuff. Oh, we don't even need any of this then. We can do... Great. So it looks like we can create a 3x3 rotation matrix with quaternion, and then we don't have to do any of that stuff. Great. So that's a lot easier. Cool. So now I'm going to go over here, and if I look over at my cone, ideally now I'm pointing in the right direction. If I go left and right, I'm still going left and right respective to my cone. So you can kind of see now when I'm applying my stuff, I'm going in the way I want to go. Not to mention up and down, which I got for free. And the reason I got it for free is because when I rotate my forward and my left, it also rotates with the up and down. And so that's there you go. That's the sort of the context of this. Now you have a camera class actually with a very limited amount of code that can do pretty much like is the first person controller. And you can add a lot to this stuff. Obviously, you can go up and down. You can add, like to do up and down, all you would have to do here is go float up and then point origin plus up to mv up. And then just have to change the camera to float up. And in the app controls, you can actually do this too, where you can set this to 0 if you want, so then it won't give you any errors. And then if you wanted to do QE, right, we want to go negative F speed. And speed. And now if I use Q and if I use E, I can go straight up and straight down. Note that the up and down vector is not changing. And so my rotation and my orientation will not affect it. So now up and down. I can go, you know, so cool. So I've got a pretty capable thing already. Awesome. So really quickly, I'm going to touch on well, actually, you know what? I'm going to do a different video to go through the instancing example, but to really kind of exemplify it here, all you're doing is, well, I'm rendering here, but imagine if I can render, I can do this, for example, for int a equals 0, a is less than 10, a plus plus, right, and instead here I can go, you know, let's call it float spacing width equals 20. Right, so here I'm going to go width divided by 2.0 plus a times width divided by 10. Or we can do even float num. Right. So now it's going to render 10 of these objects over here, apparently. Right, it's gonna go that way. Cool. So now I've got 10 of them, and in fact I can go. Let me change this to I, and this is going to be J. And now instead of, now I can put this here, right, and put J. And the idea here is that I'm basically using the same object on the GPU. I'm just calling the call on it over and over again, and now I've got, you know, all these objects that I can kind of fly through and do cool stuff to, right? If you imagine like a voxel engine, by the way, so if we, just to kind of play around with this idea, let's do 1-1. We don't need this. And I believe, what's the generated cube function look like? It's just a size and color. Right now, so you can imagine, to get to a point where we have a voxel engine, just a really simplistic one, our width is, say, num. Let's make a chunk of whatever, 32. We're going to start to hit limitations here. So let me do 8, because we're also going to add a third dimension of k. And we just have to put this into the k dimension, right? Now we've got basically 64 cubes in there. Might want to move to release. You'll notice that in release mode, these kinds of things work way faster, significantly faster. Everything from the OpenGL API to just the binaries and the runtime is significantly faster in release. So when you're doing stuff like this, you do want to actually, you can see how much faster this is. In fact, if I go up to potentially a 16 size thing, which is 4 chunks, I'll probably still be hitting a pretty reasonable frame rate. And now you can do some kind of basic, math to figure out whether or not you want to render, right? Like, say, if sine of float I divided by 16 is greater than 0.5. This is just some bullshit idea thing, but you'll see we'll start to have what's going on here? Oh. I'm just kind of trying to create an interesting... Okay, great. So we've got something. I'm trying to do this without actually generating Perlin noise. So you can see now we're kind of messing around in the I and J, and then let's add to it the sine of float K. Neat. And then let's make sure that we're actually on n2 pi, or whatever. Let's cheat. No. So you can kind of see, like, with instancing, you can get kind of creative and mess around, create some funky things, you know? And it's not all that complicated. And this is actually how Minecraft works, but a little bit more sophisticated. There are a lot of optimizations that you can do. You can imagine in Minecraft you have many more of these visible at a given time. And right now we're rendering a lot of stuff like here. We're rendering objects inside of here that aren't necessary. So you can imagine there's a lot of optimizations that you can do to change that. Another fun thing that you can do as well, and this is kind of a fun thing, is add to this and here we do theta plus equals to 0.1, and it just shows like how dynamic this can be. Let me maybe speed this up a bit so we can see the animation. It's pretty cool. Let's see where my computer craps out. This will probably not go particularly fast, but it's okay. I'm getting like 58 frames per second here. So yeah, instancing is pretty powerful, pretty fun. Not too much kind of to say more than that at this point. So I guess I will skip the other project. So hopefully this will give you a good idea of how the mesh manager is working. Or maybe I'll go through it really quick and I'll create another video. But yeah, so now with this you should be able to create a video, create a camera, move around, understand how to apply projection matrix, understand the difference between an orthographic projection matrix, and even how to instance objects like this little mini voxel engine that we put together in basically like an hour and a half. Cool. Thanks for watching. I know this one I bumbled around a little bit, and hopefully the pauses helped you guys out and cut out some of the unnecessary per the feedback I've received. All right. Thanks again for watching.